If you have been a developer for quite some time, you may have noticed a strange quote-unquote bug whenever we perform math with certain decimal point values. Now, the reason why I'm putting air quotes around the word bug is because this is not the same kind of bug that we see whenever our code breaks, or if our graphics are not rendering, or if we're designing a game and something unexpected is happening. No, this is not an issue with your code or your project. It's actually an issue with how our computer systems perform math. The issue I am getting at here are small inaccuracies or discrepancies that can occur whenever we are performing any mathematical operation with some decimal point numbers. For an example, if you create a new file with any programming language that you typically use, whether it's Python, Java, or JavaScript, and the example you're seeing on the screen right now is in Python, but if you try to add the numbers 0.1 and 0.2 together, and then display the result, instead of seeing 0.3, which is the correct and expected output, you're actually going to see 0.3, 000, 000, 000, 000, Now, you're probably wondering, well, wait a minute, that's technically not correct. That's a very, very, very tiny bit larger than 0.3. So why does this happen? Well, it comes down to mathematics and how our computers understand math. You see, math is infinite. Infinity is a very important concept in mathematics. We can technically count to infinity in a positive or negative direction. But you see, computers can only understand numbers that are so large and so small. But why is that the case? Well, computers use a base 2 numbering system called binary. And if you're a fan of the Matrix, binary is just those ones and zeros that you consistently see. And speaking of those ones and zeros, those are all called bits. And our computers, whenever we are working with numbers, they use a system called floating points, which has a limited space of typically 32 to 64 bits. Now, back to the concept of infinity, why can't our computers understand this? Well, it's a similar reason as to why we can't write an exact value for 1/3. Because 1/3 is just 0.33 repeating, but we stop writing those extra digits at a certain point because there's just no reason to. We know what 1/3 is. But in a computer, we are restricted to 32 or 64 bits of space to represent these numbers. And a bit is a 1 or a 0. A nibble is 4 bits. And 8 bits make up a byte, and then you get into kilobytes and megabytes and so on and so forth. So, what is going on with this floating point system? Well, whenever we are working with decimal point numbers, we are taking up more space to represent those numbers. And there are certain times where certain decimal point values can become inaccurate due to rounding. You see, whenever we are using the system floating point to represent numbers, we are storing these numbers as an approximation because we are only working in a constrained or limited amount of bits, so we are forced to make a rough approximation. But we round it so that way whenever we display our number in output, we see the correct number. But sometimes this rounding is not perfect, which is why in the example I shown you earlier, adding 0.1 and 0.2 will yield you a result of 0.3 followed by 15 zeros and a sneaky 4 at the end. Otherwise, 0.3 with a very small margin of error, so small In fact, you are likely to overlook it if there were other numbers rather than just zeros in that output. And if you're curious on how small that margin of error is, it is exactly 5.551 times 10 to the negative 17th power. So it's a pretty insignificant inaccuracy there. Well, I would actually be wrong depending on what we are doing. For an example, you might be working in some sort of finance firm or somewhere that deals with money, or just about any project or context that deals with a lot of high precision values. And if this is a career like finance or anything, you could potentially lose your job if you're not careful in how you are programming your application that calculates these numbers. Especially if it deals with money. Someone could be losing money because of this, and you could potentially lose your job because of it. So it's very important that we understand this issue and how we can work around it, which in fact we can very well work around it. In fact, in most programming languages, Python, for an example, has a library that supports arbitrary precision. And I believe in Python it's actually called the decimal library, but it is also present in other programming languages as well. So we can use these libraries to help us gain more precise values. But another way we can get around this is comparing floating point numbers. For an example, if we want to, we can write a check or an if statement in our code, checking if the sum of two of these decimal point numbers are very, very close to the expected output at a certain threshold. And in the example we were talking about earlier, with 0.2 added to 0.1, we can check if the sum of those two numbers are very close to 0.3 by simply doing a little bit of extra math to see if that sum minus that margin of error is equal to the 0.3. And if it is, then we can just proceed with that number. So rather than checking for it to be exactly the same value, we can just check if it's very close. And this can go for any margin of error, any threshold you would like. But where else does this occur? Well, this occurs in trigonometric functions that use the Taylor expansion or Taylor series. This can also occur in any root function, so square root. Actually, another example here is if you take the square root of 2 and then try to square it again, you'll get something like 1.9, so on and so forth, instead of just 2. And this breaks the law of mathematics, where if you square the square root of a number, it cancels out and it's just that number left. Well, if you try to do this in a programming language, you won't get that exact number. Instead, you'll get a very, very rough approximation that is very, very close to that number, but not exactly that number. I know I said number a lot, but this video is a lot about numbers. But the main takeaway of this video is to understand how our computers may not be able to perform some simple math like we can, or at least to the expectation that we have of it. And it's meant to inform you on how we can work around these little floating point errors that we sometimes see. And this is just to help us understand that our computers are limited in resources, and it is especially limited on how it can handle large or small numbers. And in the end, this can help you write more reliable code for your future projects. If you have enjoyed this video and would like to see more computer science related topics, be sure to subscribe, leave a like, and also join my Discord server. You may also join my online community by signing up on my website at www.houseofcode.xyz. And if you have a question that you would like to be answered, feel free to leave that in the comments section. I may just upload a video about that in the future. But without further ado, you guys have a wonderful day. Bye-bye.